So I really enjoyed the talk from Professor Bagan. Thank you so much. And so my talk is also about low latency streaming. My name's Bo. Today I'm going to talk about the performance of low latency HTTP-based streaming players. And this is a joint work with my colleagues from Bright Cove, Nabajit, and Yuri. First of all is the outline of my talk. First I'm going to introduce the context and objective of my work, our work, and then I'll introduce the evaluation framework of our low latency live streaming evaluation. And next I'm going to present the test result, and finally I will conclude my talk. So first of all, we all know that the current traditional HOS and the Dash player, they introduce a significant delay, around 30 seconds, and this is not acceptable for time-sensitive applications such as live sports streaming. So such high delay are caused by many factors. For example, the media segments are too long. For HOS, the segment length could be as long as 10 seconds. So we know that a segment cannot be played until it is fully generated on the server side. And second, transmission protocols such as HTTP and RTMP add another 1 to 2 seconds delay. And third, the player side buffering is another important factor of the delay. So we know that the player has to buffer 3 to 4 segments before it can start streaming. So to reduce the latency, the industry has proposed two technologies, low latency Dash and low latency HOS. And one thing to note that is that I'm not talking about the real-time communication using real-time streaming using technologies such as WebRTC. So for real-time streaming, the latency should be below like 1 second. But for low latency Dash and HOS, any HTTP-based protocol, the latency should be around 5 seconds. So key design principle of low latency systems. On the server side, the server needs to encode and push video in smaller chunks, for example, 1 second out of 4-second segments. So on the client side, the client needs to request a segment as soon as the first chunk becomes available. And in this way, we can control the end-to-end delay to be under 5 seconds. So the objective of our work is to evaluate the existing implementation of low latency HOS and Dash systems. So through our experiment, we try to understand the trade-off between live delay and also other QoE factors. So we also want to understand how mature the current implementation of low latency systems are. Next is the evaluation framework. So we use a pretty standard live encoding and streaming workflow. So on the server side for low latency Dash, we use OBS Studio to generate the live source stream. And the source stream is received by FFmpeg, which acts as the low latency Dash packager, which generates the low latency Dash manifest and also the media segments. And then those stream data are sent to the low latency Dash streaming server, which is Node GPAC Dash. It's a GPAC software. And for low latency HOS, on the right-hand side, we also use FFmpeg to generate the live source stream and send it to Apple HOS packager, and then generate the low latency HOS playlist and also media segments, and send it to Apple HOS server. So on the client side, on the player side, we run all the web players on top of Chrome browser, and then we run Chrome browser on top of a network emulator called Mahi Mahi. So how the network emulation works is the network emulator is a container, so it hosts. We run Chrome browser on top of that emulator, and emulator has a virtual link which reads the network traces, real-world network traces, and control the the data rate, the packet, the speed that packets can go out of the virtual interface, and in such a way that the low latency player and Chrome browser, their bandwidth is limited by the emulator. So for the players, we use Dash.js. There is a default Dash.js algorithm, and we also have two machine learning-based ABR algorithm called low on latency LOL and learn to adapt L2All. So we also use Shaka player. We also test Still player, and for low latency HOS, we test HOS.js. We also use the LOL and L2All algorithm, which are implemented by University of Klagenfurt. And we also use Shaka player for low latency HOS test. So for all the players, we use their default demo page. For Dash.js, there is a low latency demo page. So we are using their default configuration. So we are not configuring, we are not optimizing or just using their default values. Okay, next is the server-side setup. So on the test stream, we use Big Buck Bunny, 45 seconds. This 45-second video is looped for each 10 minutes streaming session, and we encode the Big Buck Bunny using 4 live encoding profiles. Codec is H.264, and video resolution ranges from 432p all the way to 1080p HD. So video frame rate is 30 FPS. Bit rate is about 1 megabits per second to about 5 megabits per second. So this well covers the dynamic range of the available bandwidth in both the two network traces we're using, which is Verizon LTE network and also the T-Mobile LTE network that comes with the Maki network emulator. Sorry. One more thing is the media segment duration is 4 seconds. Media chunk duration is 1 second. Network emulation, we use Maki emulator to emulate real-world network condition, and we use 2 traces, T-Mobile LTE and Verizon LTE. And this diagram shows the how dynamic the 2 network traces are. The network bandwidth, so they fluctuate significantly for both networks. So the maximum bandwidth is about 40 megabits per second to 60 megabits per second. But the lowest bandwidth for both networks, they drop to 0. 12 kbps is almost 0. So it shows how dynamic and harsh these networks conditions are. Next is the test result. So first is the result for T-Mobile LTE network. We use we show two important QoE metrics, the live stream bitrate on average over time, and also the live latency over time. So we use a bunch of other metrics, but we only show these 2 metrics here. So we will first look at the low latency dash, the stream bit rate. So on the top left corner, we see that all the players, they change bit rate quite frequently during the 10 minutes session. And this is particularly true for the Dash.js default algorithm and also the low latency, the low on low LLP algorithm. And all the players, as we see from that figure, they change bit rate quite frequently during the hard time when the network bandwidth drops significantly and also fluctuates badly. In the about 200 to 300 seconds, that area. Also on average, TO player achieved the highest average stream bitrate than other players. But if we look at the top right corner, the low latency HOS player, things are different. The low latency HOS player, they switch frequency, bitrate less frequently than the low latency dash players. And this is partially because the test player, four out of the 5 test players are HOS.js and its variants. HOS.js maybe by its design prefer to switch bitrate less frequently than other players. So that's probably why we see fewer frequencies, bitrate switches than the low latency dash. And next, if we look at the bottom left, the latency over time, we see all the players was able to maintain low latency throughout the 10-minute session. But however, there are still some latency spike in the middle of the session. That overlaps with the high bitrate changes period when the network is bad, network condition is low and fluctuating. So we see that the player got completely stuck and the latency climbs up as a result. And then the player has to reset the stream. That's why we see the sharp drop of the latency at the end of the hard time. And one more thing is for TO player, the black line, which is flat at about 6 seconds. So that's higher than other players, which is about 3 to 4 seconds. So the flat line and slightly higher latency implies TO player, they deliberately play behind the live edge, so it has more buffer and higher capacity to accommodate the network jitters, and also allow them to rebuffer less and achieve higher streaming bitrate. And next is the result for Verizon LTE network. The results are quite similar to the T-Mobile network, but Verizon network is slightly worse than the T-Mobile one. So we see all the average bitrate or whatever are lower than the T-Mobile results. But there's one thing I want to note is that on the bottom left plot, the TO player, so their latency level is not flat, unlike the previous result, but it's like a staircase. So it was initially low, and then at the start of the difficult time, high bandwidth, highly dynamic period, we see that the latency starts to go up and stay at a higher level, and there is another spike after that. So it reaches about 30 seconds, the latency, and stay there until the end of the session. So it was never able to bring the latency back down to low latency. I would think this is something that improvements may be needed. And next is the performance statistics. We have all the metrics. TO player achieved the highest average latency, and -JS default and -JS LLP, they achieved the lowest latency. The number of switches, -JS default and LLP, they have the highest number of switches and rebuffering events. And also the object downloaded, they're also the highest. And for HOS.js, for HOS low latency, we see all the number of media object downloaded are higher than low latency HOS, and this is because the low latency HOS players, they download individual media chunks instead of, while the low latency Dash players, they download the segments. There are more chunks than segments. So there's some observations from our experiment. Number one, we found that even though all the players, they were able to maintain low latency most of the time, some players fail to stream with low latency when network condition is bad. And second, all the players, they frequently rebuffers when the network is slow and dynamic. And we feel that ensuring continuous and smooth playback is more important than achieving higher average bit rate and reducing latency for low latency player. As long as we can maintain some kind of low latency, I think it's good. I'm almost done. And third, we found that some players, they double download from 2 renditions in hope of avoiding buffer underrun. And our results shows that this strategy does not work very well in practice, but it could lead to unnecessary complexity and bandwidth waste. And then some players, they switch bit rate too often. That could lead to reduced qualitative experience. And then some players, they change playback speed too often, while others stick to the natural speed. This is good for QoE. And finally, all the players show better performance than our old study conducted 2 years ago. And particularly HOS.js shows the greatest improvement among all. Yeah, that's about my talk. Yeah.
Thank you very much, Bo.
Thank you. Any questions?
Any questions or remarks? Maybe somebody from TheoPlayer would like to have a comment?
We don't change the latency. Well, we don't reduce it.
Can you use the microphone? Because I think there is one at your disposal.
For me, the results make a lot of sense because by default, we will not tune to a specific latency. So what we do is actually optimize for viewer quality. So what we do is we keep the latency which we think is the safest one, unless if you tune it down with the API. And we make sure that you play smooth. So, I mean, the statistics showed that we did not stall on Dash. That's for me a bit more important than having 1 second less of latency.
Yeah.
Thank you.
And yeah, one last thing to mention is that I'm using the default configuration on the server side, on the encoder side, on the player side. So there's still lots of room for the players to optimize their QoE performance. So my result is only for reference. It's not. I don't want to reach any conclusions. Yeah, that's all. Thank you so much.
Thank you very much, Bo.